Hi, everyone. I'm Jeff, and I thank you for taking time to listen to this session on high performance computing. HPC is expanding beyond scientific and academic communities into many industries. In the commercial sector, for example, leading manufacturers are using HPC to advance a range of products from creating more sustainable personal and consumer products to designing safer cars and planes. This session will describe 5 paths to HPC infrastructure for hybrid cloud, supercomputing, in-house enterprises, containerized machine learning, and edge computing. Each path will be described in terms of growth potential, partnerships, and use cases. My agenda here is pretty straightforward: supercomputing, enterprise, cloud, containers, and edge. The fact is that once you start on any one of these paths, you can easily diverge into multiple paths depending on your business. Each section provides a blueprint for being successful with HPC. Some of you might already have an HPC environment in place. Whether you do or not, compute intensive and data intensive workloads today are driving the need for a stronger platform across new environments from the cloud to the edge. So here I have the top three best practice guidelines for your consideration. First, understand what requirements you might have for your high performance data analytics workloads and where all the data will be stored. That will certainly influence where you need to run an HPC stack. Second, evaluate your container usage across the environments that you support. You want to maximize application performance regardless of where the containerized applications are running, so having container management in your HPC environment is a must. And third, consider your hybrid cloud and multi-cloud environments. You don't want to be locked into a particular cloud environment, but will likely want to burst HPC jobs to the cloud. Here are some interesting factoids from the latest Hyperion Research report, which provides a good portrait of the HPC market. The return on investments, including hardware, software, and services, remains very high, estimated at 507 US dollars in revenue per every dollar spent. Worldwide revenue continues to grow, although due to COVID in 2020, there was a slight dip. There is a growing need for cloud-based HPC tools and services as demand for faster answers to complex problems are needed. And one of the biggest drivers of HPC across core, cloud, and edge is AI and machine learning. Success in HPC is often tied to success in data analytics. So the first step on the left is to understand how and where data is being captured and stored. We need to understand where the analysis will occur and how much data movement might be involved. To get to an end game where we have a production grade application that generates iterative and practical insights, it all starts with data science and modeling. Predictive modeling that relies on machine learning will eventually lead to unexpected inferences that could have a major impact, positive impact, on the business and the services provided. HPC infrastructure powers the data science that produces positive business results. I'm going to start by addressing the supercomputing market. These opportunities are largely IHV driven. So we are talking about the large supercomputer vendors like HPE Cray, Fujitsu, Lenovo, Dell. Many of the installations are at international research labs, such as NCAR, the National Center for Atmospheric Research, or NOAA, the National Oceanic and Atmospheric Administration, or the IRIS Center for High-End Computing. Supercomputers can be expensive to maintain, but great strides in lower cost, ARM based supercomputers are coming into the market, and being used in universities like the University of Bristol in the UK. And while lots of investment is required to use these supercomputers, the ROI can be quite significant. So, this is my own analysis based on the most recent Top 500 Supercomputer report from November 2020. And what it shows is the breakdown for those supercomputers that rely on a commercial operating system, represented by 107 supercomputers in the list. SUSE and Cray Linux environment, which is a SUSE derivative, have a 41% majority share, followed by Red Hat at 32%, BullX at 17%, and Ubuntu at 10%. A slightly different look at my analysis of top 200 supercomputers, vendor supported OS usage, reveals that SUSE and CLE still have the majority. On this pie chart, I'm only showing the commercial OSs, so the percentages in the chart do not add up to 100%. Other non-commercial OSs including CentOS or unspecified Linux, TOS, which is the Trilab operating system, and others gain more share in the smaller supercomputers. So I mentioned that ARM-based supercomputing is garnering more attention. Well, here are two examples. NVIDIA is introducing a new ARM-based processor called Grace as HPC workloads grow exponentially. The Swiss National Supercomputing Center has already announced plans to build Grace-powered supercomputers in support of national scientific research efforts. The Catalyst UK program brings together HPE, ARM, SUSE, and three leading UK universities to establish one of the largest ARM-based supercomputer deployments in the world. The goal of the program is to propel the ARM HPC ecosystem and exascale computing in the UK, and to date, the performance testing that has been done has been extremely positive and productive. The exascale race will drive new technologies into the HPC market. For those unfamiliar, exascale refers to a performance measurement of one exaflop. That's exaflop. An exaflop of performance equals a quintillion floating point computations per second. And a quintillion, if you don't know, is a 1 followed by 18 zeros. In other words, it's a really, really big number. It's a performance metric that has been hard to attain, but exascale computing combined with an ability to handle both traditional high-performance computing and AI gives researchers an unprecedented set of tools to address big, complex problems. These breakthrough research projects range from developing extreme-scale cosmological simulations to discovering new approaches for drug response prediction to discovering materials for the creation of more efficient organic solar cells. The Leibniz Supercomputing Center near Munich has a high-end supercomputer called SuperMach. One project they have involves simulations of a seismic wave field during a potential earthquake in northern Italy. By understanding the effects of seismic activity, we can better be prepared in case disasters like these do occur. Tokyo Institute of Technology's cluster-type supercomputer called Tsubame was launched in 2006 as a supercomputer for everyone, for cutting-edge research. Upgraded over the years, the current Tsubame is widely used by the Institute, external research institutions, businesses, and other organizations. And you see some examples here from simulating human organs to predicting traffic congestion to weather forecasting and even solving the mystery of baseball trajectories. That's a link to a recent article on the slide here that appeared in HPC Wire. So each day, about 100 tons of asteroids, real tiny ones, hit the Earth. At night, they appear as shooting stars, and most burn up in the atmosphere anyway. But each year, about 2 asteroids the size of a car hit the Earth. And every 10 years, an asteroid the size of a two-bedroom house hits our planet, potentially causing lots of damage or at least a pretty big impact crater. The NASA Asteroid Threat Assessment Project monitors these NEOs, or near Earth objects, and develops response plans that can project or protect lives and property. And I show this because the supercomputer that they are running here um, has been around a long time. It's run through some upgrades itself, but it does run Suse as the operating system platform. The next area to talk about is HPC for the enterprise. And the takeaways here are that HPC infrastructure is being driven into enterprises today and will likely increase in the future. Whirlpool, for example, brought their HPC in-house to help design cost-effective refrigerators that could iterate on thousands of design parameters prior to building physical prototypes. That's the expensive part of the whole process. This ended up saving money. Also, with heavier usage of AI and machine learning applications in the enterprises and the desire for faster results, this in turn drives the need for a stronger platform and a stack inside the enterprises. Real, tangible results and benefits are starting to be realized by bringing HPC inside the enterprise. HPC and enterprise convergence is occurring now, and it's speeding up. Competitive forces are driving companies to aim more complex questions at their data structures and push business operations closer to real time. And in order to get those fast business results from analytics and modeling, enterprises are realizing the need for HPC in-house for scalability and for ultra-fast data movement. Also, and research labs and commercial sectors are converging around a shared need to support extremely data-intensive machine learning workloads. And this pie chart shows the breakout of HPC infrastructure across industries. We've seen some good growth in commercial industries, and commercial enterprises represent 58% of the total HPC platforms. For things like appliance design, ultimately, using an HPC infrastructure for simulations and modeling leads to faster time to value with highly effective virtual design spaces. In the end, this saves time and money because prototypes are used for validation and development. It also improves customer satisfaction with higher quality products that include more customer design features. Researchers and scientists use powerful HPC clusters to perform advanced materials research. Very strong yet lightweight materials are crucial to automotive and aerospace manufacturers, particularly if they are used in extreme temperatures. Developing such materials requires a deep understanding of their underlying properties, and understanding these properties requires time-consuming computational processes on a massive scale. The next area with a growing reliance on HPC is the cloud. Not only does the cloud enable HPC resources to be available to scientists around the world, that accessibility drives cloud-based HPC growth. Public and private cloud vendors have added HPC-specific instances and tools. Bursting is the most prevalent use case for the cloud today to gain resources and processing power on demand. And now HPC in the cloud has expanded outside of traditional areas to include retail customer profiling, government and finance fraud detection, manufacturing and animation simulations, and weather prediction. A number of our partners, like Crunchard, which is a South African company, are offering new HPC-based models for the cloud. Hyperion Research put together some compelling numbers for the HPC in the cloud market. Despite the small dip in the numbers last year due to COVID, the growth in spending is strong. Major drivers for this include dramatic improvements in supporting HPC jobs, easier and more cost-effective deployment, and a big increase in running machine learning workloads in the cloud. HPC applications can scale across thousands of compute cores. In a cloud environment, they can run as a 100% cloud native solution, shown on the left, or burst to the cloud on demand, shown on the right, whenever additional resources are required. Bursting is the most prevalent scenario we see out there today, preserving the on-premise HPC environment already established. So looking at the all-in scenario on the left, this is ideal for supporting HPC workloads closer to where the data might be collected in the cloud or at the edge. Essentially, a mini HPC environment is established within the cloud, and that includes the head and compute nodes as well. This ideally helps lower cost while still realizing high performance and removing the bottleneck of high latency data movement. On the right-hand side, the HPC bursting scenario that addresses changes in capacity needs on-premise by extending the jobs to the cloud, giving on-demand scale and flexibility. The Hyperloop incorporates magnetic accelerators and compressed air bearings to remove frictional forces that normally plague the use of wheels, and design simulations address the complex dynamics that are here and anticipate operational maintenance and hard to measure variables such as earthquakes, power outages, and passenger fluctuations. The design has to be safe, reliable, affordable, and self-powered. In short, it gets really complicated. As an open source design project, engineers and data analysts everywhere around the world contribute to the Hyperloop design. So making HPC accessible through the cloud enables the broader team to contribute. In the pharmaceuticals industry, high performance data analysis predicts treatment results and drug interactions with patients, improves drug design and discovery, and helps uncover biological origins of diseases. Data analysis integrates different types of biomedical and healthcare data with existing business processes using machine learning, all with HPC infrastructure to power the workloads. My next area is around a containerized approach to migrating HPC workloads from one environment to another, scaling these workloads, and in the end, obtaining faster results. While Kubernetes itself lacks the high performance scheduling capabilities that are needed here, there are a number of HPC container platforms like Rancher, Singularity, and UberCloud that are addressing that performance. Data scientists today are relying on using containers across all environments, so it becomes super important to have the same container management capabilities within HPC environments as well. Containerized workloads in HPC environments exemplify scale and performance wherever those applications end up running. So to become a good container management solution for HPC, it must be designed for performance and support hardware such as accelerated GPUs. The solution has to work with different resource managers, Slurm being very popular, and also Altair PBS, Bright Computing, and others. There should be a nice interface for managing the jobs and services, and everything should be in place with security and compliance in mind. There are two main HPC related communities that SUSE is heavily involved in. One is OpenHPC, which provides an open source stack of HPC components for groups wanting to adopt the environment quickly and easily. The second is shown here, OpenACC Accelerator, which for us at SUSE helps our customers simplify access to accelerator technology. With the advent of compute and data intensive applications that are powerful and need to be ported across many different operating environments, this community promotes a directive based programming model that is designed to provide that performance and portability. The portability is needed across CPUs, GPUs, and other accelerator hardware environments. As a market leader in genetic sequencing, Illumina's research drives work on disease, drug reaction, and agriculture. Rancher build helped them provide a migration path for a system with 25,000 HPC computing cores and 20 petabytes of storage. As traditional HPC distributes compute over many nodes, there are smaller numbers of large files with data transfers between multiple nodes. Open source container platforms like Rancher are designed to be simple, fast, secure, and are optimized for these HPC workloads. The last path or approach I want to cover is edge computing. Using containers and Kubernetes clusters are a natural fit here. And now high performance data analytics workloads are starting to drive the need for stronger platforms even at the edge. As more data is gathered by more sensors, analytics at the edge is more desirable to avoid lots of data movement. So having a strong HPC infrastructure for edge devices that relies on Kubernetes and container management is becoming a bigger requirement in many verticals. In the context of continuous integration and development, data engineers are faced with the challenge of building workflow pipelines that are adaptable, available everywhere, and reproducible without constant reconfiguration. A flexible AI infrastructure is needed as organizations evolve towards edge computing. An innovative project that we started at Suse builds a micro infrastructure that removes the complexity of the installation, configuration, and execution of any AI platform so that users can focus on things like predictive modeling and inferencing. That's what this K3 AI community project is all about, producing a reference architecture to help data scientists. In energy production, HP simulations and modeling help reduce the cost and risk of future operations, and machine learning is revolutionizing the way we produce, transmit, and consume energy and helps to limit environmental impacts. And this helps to optimize supply and demand and enables proactive maintenance. Energy smart grids powered by AI and machine learning continuously collect overwhelming amounts of data from millions of smart sensors nationwide to make timely decisions on how to best allocate energy resources. In the automotive industry, software defined vehicles incorporate AI in many ways, and in designing the vehicle itself, a high performance computing environment is used to run simulations and do performance tuning throughout the whole process. Using an HPC integrated design environment helps reduce design times, enabling engineers to create and test their ideas quickly and with few hardware prototypes. SUSE Linux Enterprise High Performance Computing is essentially the operating system plus a collection of scientific and computational libraries and a set of popular HPC tools. SUSE provides fixed level support for these tools that are packaged in what we call the HPC module, and the module is available with every OS subscription. The OS and the tools are available for both x86 and for ARM64 architectures. Now here, I summarize all of the tools and the libraries that are delivered as part of the SUSE HPC module, which is available again as part of every SUSE Linux Enterprise HPC subscription and updated more frequently than service packs. Some key items to note: SLE HPC and the HPC modules support both x86 and ARM64. Slurm is available here. It's one of the most popular job schedulers and workload managers out there, and is supported by SUSE. Performance monitoring tools such as Ganglia are included in the module, and there are several very popular third-party packages that have been curated on our SUSE package hub that can be used in this same HPC environment. When comparing our SUSE HPC module to the Open HPC stack, there are a lot of similarities, and that's on purpose. In fact, OpenHPC is tested at the Texas Advanced Computing Center in Austin on both CentOS and OpenSUSE Leap for both ARM and Intel AMD architectures. So you can see that comparison there. So let me finish up with a few conclusions. SUSE delivers an HPC platform that makes those solutions better. It's easier to develop, faster, more manageable. In fact, all of the examples I used on the slides previously are all SUSE customers. Businesses around the world today are recognizing that a Linux-based HPC infrastructure is vital to supporting the analytics applications of tomorrow. And HPC is not just for scientific research any longer. It's being adopted across banking, healthcare, utilities, manufacturing. So it's fairly widespread. So with that, I'd like to thank you for joining and for listening, and have a great day. Take care.